Let's begin this benzene chapter with some naming. We have been running across some of these compounds before. Maybe we should have done this naming a while back, but here we go. Let's try this now. There are some parent rings that you should look for when you have a benzene ring with substituents that you're trying to name. If any of these substituents are located on the ring, then you should choose that as the parent ring. For example, if you see benzene with an amino group on it, you should not name it aminobenzene, you should name it aniline. Same thing with the methyl group, that's kind of tricky. If you see a methyl on a benzene ring, you should name it as a toluene. If you see a higher priority group, like if you have an aldehyde and an amine, or an aldehyde and a methyl and an amine, you would name it as the higher priority group, which would be the aldehyde in this case. So get in the habit of looking for one of these parent rings when you're naming benzene compounds. If you don't see any of these substituents, then you would name it as a benzene. Benzene would be the parent ring, and then you would just list the substituents that are on that. If one of these is on the ring, then the carbon that it's attached to is carbon 1, and then you just have to choose whether to number it clockwise or counterclockwise, depending on where the other substituents are located. We have mentioned this before as well, especially in looking at NMR signals, but 1,4 dye substitution on a benzene ring is para, 1,3 dye substitution is meta, and 1,2 dye substitution is ortho. And the presence of some of those benzene puns on our homepage probably has gotten you used to those terms by now. This is not as helpful when you have more than 2 things on the benzene ring, but we have some examples where we have 2 things on the benzene ring, and so we can try naming these both with some numbering and by calling it ortho, meta, or para. So as we go through this chapter, if you want to pause the video to try these problems yourself, that would probably be a good idea. But I will just keep going here. This first one, I have a choice of naming this as a benzoic acid or as an aniline. A carboxylic acid is higher priority than an amine, so I'm going to name this with the parent ring being benzoic acid. And then that makes that carbon 1. And then the amine group is on carbon 4. So that would make the name of this compound 4-aminobenzoic acid. That's the numbering way to do it. You could also call it para-aminobenzoic acid. Chloro is not one of the parent rings that we have to choose from, but methoxy is. A benzene with a methoxy group on it is called anisole, so that's going to be our parent ring, and that would be carbon 1. And then, of course, we need to go this way to get to the chlorine faster, or at a lower number. So this would be 3-chloroanisole. It could also be called metachloroanisole. Sometimes instead of the meta or the ortho or the para, you just see the one letter, like P for para or M for meta. I wanted to warn you about that. All right, this compound over here has a methyl group as its parent ring. Its parent ring is toluene. And toluene is benzene with a methyl group on the number 1 carbon, so that is carbon 1. So this would just be 2-ethyltoluene. You could also call this orthoethyltoluene or O-ethyltoluene if you would like. We again have a benzene ring with a carboxylic acid on it as the parent ring, making that carbon 1, and the chloro group is on carbon 3. So the numbering way to name this would be 3-chlorobenzoic acid, or we could also call it metachlorobenzoic acid. The question asks about the per acid or the per oxy acid. We have seen this before in some of our reactions. This is metachloroperbenzoic acid, which we have been abbreviating MCPBA from our chapter where we were making epoxides. So the M in that compound stands for meta, for this ortho-meta-para naming system. For these compounds, you could describe things as being ortho to each other or meta to each other. Like for this first one, you could say that the nitro group is meta to the bromo group, but using ortho, meta, and para in the name would just get too confusing because you don't know which groups you're referring to. So for these ones, the official name should just be using the numbers. So I'll have you try these and pause the video if you'd like. So for numbering, we're going to have to start with the ethyl group for this one, because then we can have a group at 2 and a group at 4. If you start with the bromo, you'll have the nitro group at 5, which is a larger number. And if you start with the nitro, you'll have a group at 3 and a group at 4 instead of a group at 2 and a group at 4. So 1, 2, and 4 are the lowest numbers you can give these substituents. So it's best to number it this way. Then when you list them, you can list them in alphabetical order. That's the better way to do it. So the bromo comes first alphabetically. We'll call this 2 bromo, 1 ethyl, 4 nitrobenzene. The parent ring is benzene because there's no other parent ring in this system here. So this is 2 bromo, 1 ethyl, 4 nitrobenzene. For this next compound over here, we should have the bromo group be at 2, like one of these side ones should be 1. So we could have a 1, 2, 3, and 5. That's the lowest numbers that we can have. So either of these groups will give you a 1, 2, 3, 5, which is the lowest possible numbering that you can get. A 1, 2, 3, and 5. That's the lowest. So both of those would give a 1, 2, 3, 5 numbering system. So that's kind of a tie. And then you can break the tie by using alphabetical order. The ethyl group would come first before isopropyl in alphabetical order. You would use the I for isopropyl. So this one has an I as the first letter. This one has an E as the first letter. And so the ethyl wins the final tiebreaker. So we're going to make this 2. This is not going to be 1. This is going to be 3. And this is going to be 5. The bromo comes first when you're listing it. So B comes before E. Then we have 1, 5 diethyl. And then we have 3 isopropyl benzene. All right, so this one over here, I think we want a 1, 2, 3 numbering system. If we started with the bromo, we would have a 1, 2, 6 or 1, 2, 6. That's not as good as 1, 2, 3. So we're going to have to start either with the chloro or with the propyl. The chloro wins alphabetically, so I think we'll start here with this being 1, this being 2, and this being 3. Okay, that looks a little bit better. All right, this last one is a little bit tricky because benzene is not our parent ring for this one. If you'll notice, we have a different parent ring besides benzene. We have toluene as our parent ring, which makes this definitely carbon 1. And then the numbering, it's symmetric, so it doesn't matter actually which way you go around the ring. You're going to have a 2, a 4, and a 6. So this would be 2, 4, 6 trinitrotoluene, also known as TNT. Another thing that we've come across before is naming something that has a benzene ring attached to something else that is bigger or for some reason higher priority, and the benzene ring is a substituent, and that is called a phenyl group. If you have a benzyl group, that means there is a benzene ring with an additional carbon. So it's kind of like a toluene group attached to something. That's called a benzyl group. And when you're drawing things, if you want to, pH would abbreviate for just a benzene ring. And you can use AR for an aryl group. An aryl group is an aromatic group that's attached to something as opposed to an alkyl group, which is a non-aromatic carbon group. An aromatic carbon group would be called an aryl group. So you can use that as an abbreviation as well. So here we have a little bit more naming where we have benzene ring as a substituent. So this particular first compound is a carboxylic acid. That's a higher priority than alcohol. So we're going to name this as a carboxylic acid, which puts the carboxylic acid at carbon 1. We have a 5-carbon carboxylic acid, and we will just name that as the pentanoic acid with some substituents. All right, so that is 3-hydroxy 5-phenyl pentanoic acid. This next compound here, we have a cyclic ketone. So it would definitely be harder to name this cyclic ketone as a substituent. We'll use this benzene ring as a substituent. This will be a substituent here, and we're going to number this cyclohexanone ring here. Remember, cyclohexanone has the ketone at the carbon 1. So we should make that carbon 1, and then we should go this way so that we have the other substituents at 2 and 5 rather than 3 and 6. We want lower numbers. So this is the better way to go with the numbering here. So 5-benzyl 2-methyl cyclohexanone. So benzyl is a little bit less systematic, less IUPAC friendly. So one place that you would see benzyl is something like this, where you have an ether, because remember, ether are a lot of times called by their common names. So if you have an ether and you want to put 2 benzyl groups on there, remember the benzyl group has a carbon and then a benzene ring. So make sure you draw these particular carbons and don't just have diphenyl ether, have dibenzyl ether. So here, if you need the phenyl ether, that would just be the benzene ring without the carbon, and then the butyl group is a 4-carbon chain. So we have butyl phenyl ether there and dibenzyl ether over there. So hopefully those are good examples for illustrating the difference between benzyl and phenyl. Let's talk about the way that benzene reacts. It is different from regular alkenes. So we've talked about how the aromatic ring of benzene gives it that extra stability. And so benzene does not like to disrupt that aromatic ring. A regular alkene, when it undergoes a reaction, the alkene disappears and 2 things get added to that alkene. And so it happens relatively easily under mild conditions. Maybe if X and Y were both bromine, you would get the dibromo product pretty easily and pretty quickly. Benzene, however, does not want to react that way. We don't want to have a ring, or at least benzene doesn't want to have a ring, where one of the pi bonds is missing, because this would no longer be aromatic. And that's not as stable. So instead, what happens is that one of the items will end up adding to the ring, and then instead of the second one adding, the hydrogen that was on this carbon will get kicked off, and so the hydrogen is in effect being replaced by this new group. For the alkene, the hydrogens that are already here do not get replaced, they stay there. So a new thing is gotten added to the ring, but the hydrogens are still there. For the benzene, the hydrogen that was there is being replaced by a new group, and so now there are only 5 hydrogens on the benzene ring instead of 6, and there's a new group on there. And also we need very harsh conditions to get this to happen. Okay, let's try looking at the mechanism for this reaction. First of all, we'll go ahead and have the pi electrons of benzene. Those are nucleophilic, and we'll have those attack a strong electrophile. We'll give some examples of strong electrophiles that do this in just a bit, but we'll have a positively charged Y group as our representative electrophile getting attacked by these pi electrons. So I went ahead and just picked one of the 2 carbons to put the Y group on. So the one that the Y group is on, the carbon still has 4 bonds and it has those electrons. Those electrons got taken away from the other carbon, the lower carbon over here, and so this carbon only has 3 bonds. There is a hydrogen here that I didn't draw. I could draw it. There we go. So we have a hydrogen. Both of these still have their hydrogens. So that hasn't changed. Both of the carbons still have the hydrogens, but one of them only has 3 bonds, and so it is a carbocation. This carbocation is delocalized. If you want, you can draw some different resonance structures for this. I've moved these pi electrons over to quench that carbocation. That creates a carbocation over here on this other carbon. Then we can move these pi electrons down to give this carbon 4 bonds, and then that would create a cation up here at this carbon. So here are 3 resonance structures. The cation is being spread out over 3 different carbons, so that helps to stabilize the cation. Instead of having the positive charge just on 1 carbon, it's shared by 3 carbons here in the benzene ring structure. All right, so I've just picked the last resonance structure, and I'm going to go ahead and show these electrons as going back into the benzene ring. So now the Y is on the benzene ring. The benzene ring is a benzene ring once again. It's not one of those disrupted ring systems with the carbocation, so it's back to being a much more stable benzene ring with a Y group on it. The H+, you can show it as going away on its own. Actually, H+ would be associated with whatever molecules are around in your solution, so it would not be on its own. Because of that, your textbook does not tend to show the H+ flying off on its own. It likes to show different bases as grabbing the proton. It would not be a very basic base. It would not be a negatively charged base. These all take place in very acidic conditions, these benzene reactions. And so this would be maybe water, but just something with an electron pair can take the H off of the benzene ring and give the benzene back its electrons. And so the product is the same. And then we have HB with a positive charge. So here we're able to show this without showing any negative charges in the mechanism because, again, these are very, very acidic conditions that are needed for this electrophilic aromatic substitution. So between steps A and step B, which one is more difficult, do you think? Forming this carbocation or reforming the benzene ring? Hopefully you don't have to think about that for too long. This one is a much happier thing. To reform the benzene ring is really great. Disrupting the benzene ring is not so great. So this is going to be slow and difficult. This one's going to be easy and fast. So the slower one is going to be step A. So what types of electrophilic aromatic substitutions can we do? What can we put onto the benzene ring? What is Y? And it can be a halogen. You can put bromine, chlorine, or iodine on there. You need some very harsh conditions. Just using Br2 is not enough. You need a catalyst. The catalyst complexes with the bromine. So the iron is very electron poor, and so this bromine over here, remember these bromine atoms, remember the bromine atoms have a lot of lone pairs on them, and so it can donate a lone pair to electron poor iron. Iron atom is very electrophilic. One of the lone pairs could get attracted to that iron atom, and then you have a bromine with a positive charge over here. And then when you have the pi electron system add in to this bromine, then this would no longer be positively charged. And so you would have your bromine on the benzene ring, just like we saw on the previous page, stabilized carbocation, and then the hydrogen would get kicked off of here, and then you would have just the bromine on the benzene ring. So all of these electrophiles are very, very intense electrophiles. Positively charged bromine complex, chlorine complex. Iodine itself would be positively charged iodine as the electrophile. Usually you see iodine with a negative charge. So this is a very, very unusual electron poor iodine that's been oxidized. Let's scroll up a little bit and see what other kind of crazy electrophiles you can get. Nitration you can do. You need nitric acid, which itself is extremely, extremely harsh. Nitric acid is not something to mess around with, and even nitric acid is not a strong enough reactant without some sulfuric acid as the catalyst. So the sulfuric acid, it shows the mechanism in the textbook. It protonates the nitric acid and has water leave, and you have a positively charged NO2 being the electrophile. A similar thing happens with sulfuric acid. You either need some hot concentrated sulfuric acid or fuming sulfuric acid, which is sulfuric acid with some SO3 added to it. And so you have SO3H positively charged as the electrophile. So that is something that is extremely harsh, extremely reactive. And then that can put a sulfonic acid group onto the benzene ring. This is reversible. The sulfonation can be, the sulfonic acid group can be removed if you have some water that is more dilute. If you don't have concentrated sulfuric acid, if it's more dilute acid, aqueous environment, and you heat it up, it can take off that sulfonic acid group. So the H plus can add in and kick out the SO3H plus group. So other things that you can add are an alkyl group or an acyl group. All right, I'll have to fix that. It should be a Friedel-Crafts acylation or a Friedel-Crafts alkylation. The Friedel-Crafts reactions need aluminum trichloride as a reactant. The aluminum trichloride reacts with either the acid chloride or the acid anhydride or the alkyl halide in the case of the alkylation to form a positively charged carbon, which can then be a very strong electrophile. Here we have, carbocations we're a little bit more familiar with. Here is an acid chloride. Once the chloride leaves, you have this acylium ion. So you have a positively charged carbon double bonded to an electron withdrawing oxygen. So that is very electron poor, and that can add to the benzene ring. A carbocation, we are familiar with using those. Rearrangement of carbocations will occur. If you try to add something that can rearrange, it will. Also, once you add an alkyl group, the benzene ring is more reactive toward a second addition. We'll talk about that in a bit as well. And so to prevent a second alkyl group from adding, you would use benzene in excess. So then your results would be a bunch of benzene that did not react and a bunch of benzene that reacted once. And so you would just separate those, the product from the excess benzene, and you would be able to have product with only one alkyl group on it. And in addition to having really, really reactive, really corrosive electrophiles, they usually have to be heated, sometimes quite hot and for quite a long time. There are a few ways to get around this problem with a carbocation rearrangement if you do not want the rearrangement to take place, or if you want to have something put onto a benzene ring that has a CH2 group next to the benzene ring. That is not going to work very well with a Friedel-Crafts alkylation, because you would need to have a primary carbocation, which is really not going to work very well. So, and plus it's going to rearrange. Even if you can get it to form, it will rearrange. So this is not a good way to do it. Instead, what you would want to do is form the acyl group, use the acyl group and do an acylation, a Friedel-Crafts acylation on a benzene ring. And then this ketone is very reactive. You can treat it with hydrogen or with palladium catalyst, and that will, for most ketones, that would result in an alcohol, but for the ketone right next to a benzene ring, it can take the ketone completely off and give you just the alkane. You can also take the ketone completely off with a Wolff-Kishner reduction. That can be done on any ketone. It doesn't have to be right next to a benzene ring, but you would use hydrazine to turn the ketone into a hydrazone, and then you would treat it with base, and the base would take off a proton from the nitrogen and then put it back on the carbon, moving this double bond in between the two nitrogens instead of in between the nitrogen and the carbon. Then you would repeat, taking this proton off, making a triple bond in between the nitrogens, making this temporarily a carbanion, and then the carbanion would get a proton back, and you would get nitrogen gas as the side product. So let's see what would happen for this Friedel-Crafts alkylation. The aluminum trichloride would form a carbocation here. So it would complex to the chlorine, and then these electrons would go with the chlorine, and so you would end up with a carbocation. However, this carbocation would quickly rearrange. It would do a 1,2 hydride shift, giving you this carbocation, and then this is the carbocation that would be attacked by the pi electron system, and so after that happens, you would get that carbon attached to the benzene ring, giving you isopropyl benzene. So if that's what you want, that's great, but if you wanted just the regular propyl benzene, that would not be a good way to get it. Over here, the aluminum trichloride complexes with this chlorine, which then leaves, and we get our acylium ion. Then the benzene ring would add to that carbon. So the benzene ring would be acylated instead of alkylated here. It's a Friedel-Crafts acylation. And then treating this with hydrazine in base and heat would form the hydrazone and then eventually get the ketone completely removed here. So this would actually give you the propyl benzene, whereas if you tried to add 1-chloropropane directly, you would end up with the isopropyl benzene instead. So this is what we mean when we say that the acylation is a way to avoid these carbocation rearrangements. There are other ways to get alkyl groups like this onto a benzene ring that we've learned about before. We have some couplings. Remember our chapter 12 where we did all kinds of organometallic couplings. A lot of times we mentioned that the halides could not be alkyl halides. They had to be either vinyl or aryl halides. Well, now we are working with benzene. We want to put things onto benzene rings, and so aryl halides work just great for that. Here's a couple of examples over here. So we have a coupling, a palladium catalyzed coupling done with a borate group and an alkyl halide. This could be a chlorine or a bromine on the benzene ring, and then these two would get coupled together. So the 4-carbon chain that's on the boron would end up on the benzene ring. Let me finish drawing my benzene. And then this is called a Suzuki reaction. The palladium catalyzed coupling of an aryl or vinyl halide with a borate ester. That's a Suzuki reaction. We also have this capability if we use a copper organometallic, that will also couple to a benzene ring. In this case, the alkyl group is just an ethyl group. This is a Gilman reaction, the reaction with organocuprates. So these are other ways to get an alkyl group onto a benzene ring without worrying about carbocation rearrangements. All right, that pretty much does it for the things that you can get onto a benzene ring. We're a little bit limited there because there's only so many super crazy harsh electrophiles that you can make. However, once you get a few of these things onto a benzene ring, a lot of times they are more reactive and they're easier to convert to other things. So for example, an alkane piece on a benzene ring can be halogenated, but you can either use light and bromine, or you can use N-bromosuccinimide with some oxidation peroxide as a radical initializer and some heat, and you can get bromine to do a radical halogenation on the benzylic position. And then once you have a halogen on there, you can do an SN2 reaction and displace it and add other different groups on there. You just have to be careful that you don't use a nucleophile that is also too strong of a base, because the alkene that forms from an elimination is conjugated, and so that's extra stable, so it forms really easily. So you just have to be a little careful about the conditions here. We have a few samples for you to try. Okay, so we could have this nitrogen nucleophile attack. Again, SN2 reaction. it attacks. I didn't really specify the stereochemistry, but it would be an inversion probably. And then this bromine would leave. So again, a good leaving group here. So nucleophiles can knock that leaving group off, and you can attach other different pieces besides just a halogen. So when the nitrogen first goes on, it would be protonated, and then the proton would probably stay there if we are at pH 6 or 7. Remember, amines are protonated below about pH 9. So let's go ahead and draw that with the proton still there. And then we have the counterion. So these might be, you could draw them closer to each other if you want to draw the salt here. Okay, so we have sodium cyanide. This cyanide anion is not too harsh of a base because the pKa of hydrocyanic acid is only about 9, so not that terrible. And so we could probably get this carbon to displace the bromine without causing too much elimination here. So instead of the bromine here, we would have the nitrile. So you don't really have to draw these other ions. The important thing is that we have another carbon attached to our organic molecule here. So sodium hydroxide is a pretty strong base. If you do it on something that cannot eliminate, remember this cannot eliminate, because to eliminate you would need a neighboring carbon with a proton that can be removed. Here this is missing. This is just benzyl bromide. So this cannot eliminate. So even though this is a fairly strong base, it can't pull off any protons. So instead it's going to attack and give you this benzyl alcohol product. Again, if you want to, you can draw the sodium and the bromide around. That would be the other ions produced. Those would probably go away in the workup. So if you do have a proton on the neighboring carbon, we are probably going to have this hydroxide go and pull off that proton instead, and we're going to cause an elimination. So this one would not really be an effective way to get the alcohol, I don't think. I think you would get the alkene instead. Okay, another feature of benzene is that these pi bonds do not get hydrogenated very easily. Just like other things don't add to the benzene ring very easily, hydrogen does not add to the benzene ring very easily. So you can hydrogenate other things that are in your molecule without having to worry about the benzene ring at all. Add hydrogen to this compound, it's only going to hydrogenate the alkene. It's not going to touch the benzene ring. So over here you can reduce the nitrile without touching the benzene ring. And that is the compound that would result there. We would have 2 hydrogens added to each of the carbon and the nitrogen, so you would get this primary amine here. You can also reduce the nitro group here. That would reduce to an aniline. So that's another group that you can reduce without worrying about anything happening to the benzene ring. This example C is an oxidation. It's not a reduction. Forgot to mention that one. So oxidation of alkane pieces on the benzene ring happens very easily as well. And the result is the carboxylic acid attached to the benzene rings. So it doesn't have to be just a methyl. You can oxidize an ethyl. The only thing that you don't oxidize are the ones that do not have a benzylic hydrogen. So if you have a highly branched piece on the benzene ring, that will not react. So here we have a benzene ring with 3 alkane pieces on it. We have a methyl group. This can get oxidized to a carboxylic acid piece. This piece over here, since there is a hydrogen on the benzylic position, this one can also get oxidized. This one, this tert butyl group, does not have any hydrogen next to the benzene ring in that benzylic position. So this one will not get oxidized. So the product over here will still have that tert butyl group, but this one will get oxidized to a carboxylic acid, and this one will also get oxidized to a carboxylic acid. Let's go back to electrophilic aromatic substitution. So far, or at first, we just showed you what happens to plain benzene rings. So we have our chart over here. This is what happens when you just treat benzene itself with these different conditions. So you put something new on the benzene ring. What if there was already something on the benzene ring then when you put something new on there, where is it going to go? Is it going to go? Is it going to go on there at all? So it depends on what the thing that's attached to the benzene ring is. If what's on the ring is an electron donating group, the benzene will be more reactive, and so the reaction will work better. And also the new group that is going on will be directed towards the ortho or para position. If you have an electron withdrawing group, that's a deactivator, it's less reactive, and it's also a meta-director. So donating groups are activators, and they're ortho-para directors. Withdrawing groups are deactivators, and they are meta-directors. Halogens are sort of a weird case because they inductively withdraw electrons, but by resonance they can actually donate some of their lone pair electrons. And so what they do is they slightly deactivate, and yet most of the deactivators are meta-directors. Halogens are actually ortho-para directors, so they're a little bit unusual. So why would an electron donating group direct the new group to go in the ortho or para position? And you can see with these resonance structures here that there is a little bit of extra electron density in the ortho position and in the para position, and that benzene, the way it reacts is by attacking. It's a nucleophile, and so the electrons attack. So the electron-rich part of the benzene is going to be the spot that attacks. So we have all these resonance structures contributing, and you can tell that the ortho positions and the para position are the most electron-rich. The meta do not have that same electron-rich resonance contributor. Electron withdrawing groups also, if you draw those resonance structures, they affect the ortho and the para positions more strongly. But since the effect that we're talking about is now a deactivation, that stronger ortho-para deactivation leaves the meta position as the least deactivated. So that is the most active place on the benzene when you have an electron withdrawing group. Okay, instead of drawing the resonance structures of the benzene itself, let's draw the resonance structures of the carbocation intermediate of an electrophilic aromatic substitution. All right, so let's draw one where the Y is going to add to the ortho position. Since the pi system is like this, I'll go ahead and draw it up top. So here I'm drawing the resonance structures that result from adding the Y group at that ortho position. This is the intermediate still. So this is not the final result. This hydrogen would get kicked off. In the final product, this hydrogen is going to get kicked off, and then the aromatic ring will be reformed. So these are just the intermediates that I'm drawing here. And then what's going to happen is that this hydrogen is going to get kicked off, then this won't be positively charged anymore. We'll get back our benzene ring, and it will be ortho substituted. So what we're trying to draw here is just the intermediate that would lead to the ortho substitution. So here we have where the positive charge is being shared in this unstable carbocation intermediate. All right, so let's do one where this pi group is attacking, putting the Y in the meta position. So that would be the initial cation from the arrow that I drew. Let's go ahead and share it around the ring. We'll draw the other resonance structures here. You can practice drawing those as well if you want to pause the video. So here are the three that would result from a meta addition. Now we'll go ahead and do the para addition. I'll go ahead and take these electrons and add them to our electrophile. So this is the result of that first addition, having the cation over here on this carbon. We're also going to share it on this carbon and on this carbon. Let me go ahead and draw those. All right, we're getting a little bit squished here, but I have those ones drawn as well. In looking at all these resonance structures, if W is electron withdrawing, like say that W atom is very electron poor, maybe positively charged even, or at least partially positively charged, then having that W next to a carbon that's a carbocation would be very unfavored. So over here where a carbocation is next to a very electron-poor W group, that would be highly unfavored. So we have that here in this ortho substitution, and we have it again down here in this para substitution. For the meta substitution, we do not have any of the resonance structures with the cation right next to the W. So because we don't have that highly disfavored interaction, the meta would be, it's not great to have a positive charge anywhere on the ring, but it's worse to have the positive charge right next to the W. So out of the three bad options, the meta is the best. So the meta intermediates are the most favorable when W is an electron withdrawing group, because the meta resonance structures do not have the carbocation right next to the W. If instead of a W, if we had a donating group, if we put a D there for donating, then the ortho and the para are better because that carbocation is right next to the electron-rich donating group. So for electron donating, ortho and para are better because the carbocation is right next to that group. For electron withdrawing, ortho and para are worse because the carbocation is right next to that group. So keep in mind that in addition to the ortho-para or meta directing, there is an activating or deactivating component to these groups. Friedel-Crafts is one of the toughest of the electrophilic aromatic substitution reactions to get to go. And so if you have electron withdrawing groups, if you have deactivating groups, the Friedel-Crafts will not be able to go. Also, if you have a highly activating group, then the halogenation might go too many times because that is the fastest or the easiest electrophilic aromatic substitution to get it to go. Okay, so we're going to have a table of the different types of groups that could be on the benzene ring, whether they're strongly activating, moderately deactivating, how they act on the benzene ring. One thing to notice is that amines, aniline groups, are strongly activating, but if they are protonated, so anilinium ions are strongly deactivating. And these electrophilic aromatic substitution reactions generally take place in acid or in Lewis acids, where the lone pair on the nitrogen is going to get protonated or complexed to a metal, or there's going to be a positive charge on the nitrogen in these conditions. And so when you try to do an electrophilic aromatic substitution, the aniline will quickly become a deactivating group, and you will not get the results that you were hoping for. So that's what we have here. Okay, so let's take a look at what is happening in this halogenation reaction. We have halogen going onto the benzene ring, and the thing that's coming off of the benzene ring is a proton. So we have some proton around, we have the other chlorine around from the chlorine molecule, the chloride ion. So we basically have HCl as a side product. We probably have the protonated form of the nitrogen. We also mentioned that the iron trichloride is very electrophilic and it complexes with the lone pair of the chlorine. Well, it's going to prefer to complex with the lone pair on the nitrogen. That's way more reactive than the lone pair on chlorine. So you'll either have the nitrogen complex to the iron trichloride, or you could have it protonated because of the acid that's around in these conditions. We have acid, we have Lewis acid. So the lone pair on that nitrogen is going to be taken up by some of these very acidic, very Lewis acidic things in the reaction mixture. And so the nitrogen is going to be positively charged, which makes it a deactivating group and also makes it a meta director. And so the product that you would end up with from this halogenation is not going to be the para or ortho product that you might have expected if you just looked at the nitrogen and said, hey, that's electron donating. The nitrogen during the reaction is going to be protonated, it's going to be electron withdrawing, and so you are going to get the meta substitution product. And unless you work it up with some base, it's probably still going to be hanging out as the hydrochloride salt from all the HCl that's around in the reaction as well. So if you wanted to get some para-halogenation, you could convert it to the amide. So if you took the aniline that's on the ring and put an acyl group on it temporarily and made it this group, this is not going to be a basic nitrogen anymore. So this is not going to get protonated, and we could have a moderately activating group. It's not strongly activating, but it's still activating, and it still will be ortho-para directing. So if you want to get a nitrogen to direct something to a para position, it would be a better bet to form it into the amide first, and then do your benzene reaction, and then hydrolyze the amide later. Just a couple other things, notes here, is that ortho-para directors, the ortho and the para position are both activated by an ortho-para director. So you do get both. If you have a very bulky group, or the bulkier group you have, the more the more you're going to get addition at the para position, because the ortho position is more crowded, and so the bigger group you have, the more crowded the ortho position is. But you probably will get a mix, and so you'll have to purify the two of those apart if you want to get just one or the other. Also, with the activating group, I think I mentioned this a moment ago, if you have a strongly activating group like a phenol or an ether, then if you're trying to do a halogenation, that is the most active electrophilic aromatic substitution. So if you combine the most active reaction with the most active activating group, you could get more than one chlorine or bromine added to the benzene ring. So to prevent that, you should not use that iron trichloride or iron tribromide catalyst. That would be too active. So keeping in mind these ortho, para, or meta directors, let's see if we can figure out what the products of these reactions will be. For A, we have a mildly activating ortho-para director as the thing that's on the benzene ring. So I'll draw both. I'll draw the para product and the ortho. So you probably will get a little bit more of the para, but we have sulfonation taking place on both the para and the ortho position here. So this as well, we have an alkyl group, which is a moderately activating group for a Friedel-Crafts acylation. So I'll draw some of the product where it's the para product and some where it's the ortho product. Okay, so you'd get a mix of both of those. Here we have a strong activator, ortho-para director again, so we'll get both. And both of what? This is a nitration reaction, so we will get the nitro group adding in those positions. So we have 4 nitroanisole and 2 nitroanisole as our products here. Got a couple more to do on the next page here. This one is a little bit different. We have 2 groups on here. We have a phenol and we have a methyl group. Both of these are ortho-para directors. Neither one can direct para because the para position already has something there. So these 2 groups are going to direct ortho. The ortho group, this OH group, is going to be directing the bromine to go ortho to it. And let's get a different color. The methyl group is going to be directing the bromine to go ortho to it. So since the OH group is a strong activator, whereas the methyl group is more of a weak activator, you'll probably get more of the positions that the blue arrows are pointing to, the OH group directing it ortho. So let's go ahead and draw that as our major product. So we'll have that as the major product here. This other one here, I guess I was getting a little trickier on this second page. We have a nitrile group, which is a deactivator. It's actually a strong deactivator, and we have a Friedel-Crafts acylation, which we said is not good enough to be able to overcome a deactivator. So for this one, we're not going to get any reaction. For this one over here, we have concentrated sulfuric acid and some heat, so that's a sulfonation reaction, we have bromine, which is a mild deactivator, but it's also an ortho-para director. So we're going to get a mix of ortho and para for this reaction here. So these are the two products that is going to give you here. So because there's a lot of different things that you have to think about when you're doing benzene reactions, whether something is going to go ortho or para, whether something's an activating or deactivating group, and because different groups on benzene can change, so you can have a group on benzene, let it be ortho-para directing, or let it be meta-directing, and then you can change that group by doing one of those other reactions. Standardized tests seem to like to ask questions about things like that. So I have a little sample down below. So here's something that I would not be surprised to find on some kind of standardized exam. You would just see, okay, you want to take this toluene and you want to make this metachlorobenzoic acid. Which set of conditions could do that for you? And then they might have a few different choices for sets of conditions. Here I just have two different sets of choices and then an either or neither as some of our choices here. So let's take a look at this first set. After this first step, what would we have? We would have a chlorine group adding to the benzene ring. For toluene, where would that chlorine go? So toluene, that methyl group, is a para director. So the major product that you would get here, it's an ortho-para director, so you would get some of this and you would get some of this. Okay, got the chlorine over here. So after step one, you would have a mixture of ortho and para chlorotoluene. And then for the second step, this methyl group would be changed to a carboxylic acid. But you would not be getting the meta chlorocarboxylic acid. This would give you the ortho and the para carboxylic acid. On the other hand, if you took toluene and you did the oxidation first, that would give you benzoic acid instead of toluene. And then if you did a chlorination on benzoic acid, that is a meta director. It's a deactivating group. So you would be able to get the chlorine in the meta position. So yeah, the conditions for C would give the meta substituted benzoic acid, whereas the conditions for A would give just the ortho and the para substituted benzoic acid. And so the answer for this one would be C. So there's a lot of other little tricks that you can use to get benzene rings that are substituted the way that you want them to. Here's one where you can sulfonate and then desulfonate. So here we have phenol. The OH group is a ortho-para director. You can get the sulfonate, probably more of it reacting in the para position because it's a little bit bulky. Even if you get both, you can kind of clean these up and separate them and get just the para position. And then when you do the next reaction, this halogenation, the OH group is directing it to the ortho position, and the sulfonic acid group is directing it to the meta position. So both of these groups are operating in harmony to direct the bromine to be there in that position. And then if you heat this the sulfonic acid, the benzene sulfonic acid piece in a more dilute acid where there's lots more water than there is acid, then you can get this to desulfonate. So now the sulfonate group is gone and we have the bromine group in the ortho position. So it's sort of a way to temporarily block the para position and make something happen in the ortho position instead. So that's a little trick that is sometimes used with benzene. Okay, so one other cool thing that could be done with a benzene ring, specifically with aniline. We mentioned how aniline is not the most useful starting material for an electrophilic aromatic substitution reaction because the aniline becomes protonated or complex with a Lewis acid and then it doesn't react very well. It doesn't do what you want. But aniline still is useful because it can be converted to what's called a diazonium salt. So we have the mechanism for that in the textbook, but you need to make nitrous acid in situ with sodium nitrite and some other acid source, maybe hydrochloric acid. And this also needs to be done cold because this is not extremely stable. If you'll notice that we have kind of a leaving group that is N2, or a nitrogen gas can leave fairly easily. And so that makes this susceptible to nucleophilic attack. There's various nucleophiles that you can use, especially copper salts. They seem to work with this really well. So if you have a copper 1 salt of bromide or chloride or even cyanide, you can replace that diazonium salt pretty easily. That's called the Sandmeyer reaction. To get iodine or fluorine on there, you just need slightly different conditions. It can still be done. If you treat it with water, you can make the phenol from that. You can just let it warm up in slightly acidic water, or if you want it to work a little bit better, you can use copper 1 oxide with copper 2 nitrate and add that with water to the cold diazonium salt, and that will also give you the phenol. So this unusual H3PO2 or hypophosphorus acid can be added to the diazonium salt to just make it completely leave, replace it with a hydrogen instead of some other group like a halogen or a phenol. If you just want the diazonium salt to go away, you can use this hypophosphorus acid. And then one last thing that your textbook mentions is that if you have an activated benzene ring, a highly activated benzene ring like a phenol or an anisole or even aniline, you can get an azobenzene molecule. So let's take a look at that. So here we have aniline. Usually additions, like we mentioned, don't go very well on aniline, but since this is not acidic conditions at all, you can get an electrophilic aromatic substitution on aniline if this is the electrophile. And so what happens is usually the para position, because this is kind of a bulky piece, usually the para position will be the spot where it adds. You can get a little bit of the ortho product, but the para position is where it adds. And then you get a double bond between these two nitrogens and a very highly conjugated pi system. So this is known as an azo di because this highly conjugated pi system is very brightly colored. It absorbs visible light. You can get a little bit of the cis configuration of the azo group, but mostly it will be this trans and it'll be in the para position. Let's take a look at a reaction sequence that uses a diazonium salt instead of electrophilic aromatic substitutions to make this compound over here. So if you took benzene and made bromobenzene or chlorobenzene, then if you tried to add the second halogen, the first halogen would be an ortho-para directing group. So you would not be able to get this meta product by just doing two sequential electrophilic aromatic substitutions on benzene. So instead, let's go ahead and try doing one electrophilic aromatic substitution and making it a nitro group. And a nitro group is a meta director. So if we did a halogenation on the nitrobenzene, we would get that meta aromatic substitution product. Then remember that hydrogen gas can be used to reduce a nitro group to the aniline group. So this is very useful because remember, having aniline groups on benzene when you try to do electrophilic aromatic substitution, it does not work out very well at all. So having a nitro group and then being able to reduce it to the aniline is very helpful, something to keep in mind. Then the aniline can be made with nitrous acid into the diazonium salt. Okay, so we have that there. And then this diazonium salt, if it's treated with a copper salt, it can replace the diazonium group, the N2 group, with the chlorine. And so now we have the meta, the 1,3 substituted bromochlorobenzene here. So one last thing that I Again, I've seen quite a lot on standardized tests. For some reason, they do like to ask about this sometimes, is a nucleophilic aromatic substitution, as opposed to the electrophilic aromatic substitution that we've been learning about. If you have an electron withdrawing group, one or more strongly electron withdrawing groups on a benzene ring that also has a halogen on it. So we need an aryl halide like this over here. We have a benzene ring with a halogen, and there's also a strongly electron withdrawing nitro group. Nitro group is the most common. You can treat it with a strong nucleophile like hydroxide, and it will add and replace. So it'll add in here, kick out the chloride, and then if you are in hydroxide, the phenol is acidic enough, it will be deprotonated, so you have to add a proton source, especially if you have a nitro group on the benzene ring. That reduces the pKa of this phenol significantly. And so if you have a high pH, this is going to be the phenoxide ion. So just keep that in mind. If you don't have that HCl, it will be O negative over here instead of the OH group. But if you acidify it again, you can put the H group back on here and make it look like a phenol. Okay, so let's take a look at the mechanism of this. Okay, so we have our strong base, our strong nucleophile actually, and it's going to attack this carbon over here, the one that has the halogen on it. And that will push those pi electrons onto that carbon at first. Okay, so let's go ahead and keep pushing this carbanion, this negative charge, around the ring and see if we can get all the different resonance structures that it's made out of, or all the different resonance structures that exist for it. So we'll put this over here and get this onto this carbon. Now these electrons over here can actually go onto this nitrogen, and the nitrogen can put this pi electron pair onto the oxygen. So the nitrogen still has 4 bonds and it's still positively charged, but now we have the negative charge on the other oxygen rather than on a carbon. Let's go ahead and put them back and draw the last resonance structure here. So there are all the resonance structures. Put little brackets around those. So the negative charge is stabilized because it's being shared by 3 carbons and by an oxygen. And this second resonance structure here, the negative charge is right next to an electron withdrawing group, so that is a little bit more stable than it would be as well. So those are all 4 of the resonance contributors. And then for B, we're going to choose one resonance contributor to illustrate the final step, the elimination of the chloride. Let's go ahead and choose this last structure because there aren't any arrows drawn on it yet, so it makes it a little bit easier to use. So we'll put this back onto the carbon, make the aromatic ring again, kick off the chloride, and then that would lead to this product over here, and then the chloride as the side product here. Okay, so let's do, now that we've seen nucleophilic aromatic substitution and electrophilic aromatic substitution, and that is the end of that note packet, let's just take a quick look at the topic 2 from the chapter 19 where we were talking about amines. There were a couple aromatic amines at the end of the chapter. So this was on page 306, just at the very end of the chapter about amines. We took a look at some of these aromatic amines and some special reactions that they could do. And the first one's not all that useful. It's just something to let you know not to treat pyrrole with acid because it will polymerize. But It is also very reactive towards electrophilic aromatic substitution. So at the 2 position, things can get added, electrophiles can get added without even a catalyst. So we'll just take a look at that now that we know what electrophilic aromatic substitution is. And then pyridine, it's good to know that it is not very reactive toward electrophilic aromatic substitution, but it is more reactive in nucleophilic aromatic substitution. And then the final thing to consider about pyridine is that the methyl group that's on pyridine is pretty low pKa, so it's around 20, just because the nitrogen that's in that aromatic ring can help stabilize that carbanion, and so it can be deprotonated similar to the way a ketone or an ester could be and used in an aldol condensation. So let's take a look at these special aromatic ring reactions. They're not benzene, but they're aromatic amines. So let's take a look at that. So benzene, to add to an acid anhydride like this, would need a catalyst like aluminum trichloride, but pyrrole is more reactive, so it can do that without the catalyst. So electrophilic aromatic substitution means that this pi system is going to add into an electrophile. So we don't even need an acylium ion, we just need this electrophilic carbon. These will go onto the oxygen, then they'll come back down, and then they'll kick off this group over here. Let's take a look at what results. So first let's draw the intermediate. So we still have the hydrogen here. So this is the intermediate that results. It is stabilized because we have this nitrogen that's able to carry the partial positive charge. So we can have the partial positive charge is shared by this carbon over here. Let's just mark these with a certain color. So this carbon is partially positively charged. If you pull over these electrons, you'll have this carbon with the positive charge. And then if you push over the lone pair that's on nitrogen, the nitrogen is also one of the places that's sharing the positive charge. So we have this positive charge being shared by a lot of different atoms. The nitrogen especially is able to handle a positive charge. Amines can protonate very easily. Nitrogen with a positive charge is not at all unusual, and so this makes this fairly stable as far as an intermediate goes, and so that can react pretty easily. And then, so if you'd like to, you can draw the resonance structures on your own of all those 3 spots having a positive charge. Then once you're done with all the resonance structures, what we're going to do is have those electrons from this bond quench that cation, reform that aromatic system, and now we have the substitution product. So this is the electrophilic aromatic substitution reaction. We said that pyridine reacts with a nucleophilic aromatic substitution, so we have a negatively charged nitrogen here. Let's draw the intermediate when this adds in. So we'll add this very strong nucleophile into that carbon. And let's first put the negative charge on the nitrogen. So instead of drawing all the resonance structures, let's again just show where the negative charge is being shared. This nitrogen has the negative charge on it right now. If you push these over here, this carbon will get the nitrogen, will get the negative charge, excuse me. And then if you push those electrons over here, this carbon can also have a negative charge. So you have this negative charge shared over 3 atoms, one of which is the electronegative nitrogen atom, so that makes it a little bit more stable than sharing a charge on 3 carbon atoms. And then once you finish drawing all those resonance structures, you can pick one of the resonance structures, like for instance this one that we have, to go ahead and kick out the chloride. And then that gives you the product of the nucleophilic substitution and the chloride that got kicked out. If instead of a chlorine you have a methyl group here, this proton is somewhat acidic, not too acidic, but it has a pK of around 20, which if you have a deprotonated nitrogen here, that is definitely strong enough to pull the proton off of that methyl group. So instead of acting as a nucleophile, this negatively charged NH2 group is going to act as a base. It's going to put this negative charge on the carbon. And again, instead of drawing all the resonance structures, which you are free to do, you can draw all these different resonance structures. You can just imagine that in addition to the negative charge being on this carbon, if these electrons push in here, the electrons can also be on this nitrogen. Those can push over to here and put the electrons on that carbon, and those can push into here and put the electrons on that carbon. So the negative charge is being shared through resonance on 3 carbons plus a nitrogen. So that is helping to stabilize that carbanion, which is why that proton is somewhat acidic. And then this anion can act as a nucleophile and add into an electrophilic carbonyl in an aldol type condensation, or an aldol type reaction actually. So let's just draw the alcohol at first because I'm not sure what R is. So the initial thing that forms is going to be this secondary alcohol. If the R group has has a chain and it can easily eliminate, then maybe this water will be eliminated and we'll get a condensation, which would be the one where you follow this up by forming the alkene. But since I didn't specify what R is, I can't really form the alkene, so we'll just form the aldol product. So I think that these reactions that we looked at before, I think make a little bit more sense now that we've covered electrophilic aromatic substitution and nucleophilic aromatic substitution. So I wanted to go back and take a look at those reactions that we skipped last time. All right, and I think that that is enough benzene reacting for one day. I hope that you found this helpful.